Hi, this is for Chem 102, section 10.7. So in this section, we're going to talk about another way to find the enthalpy of a reaction. We've been talking about several ways in which we can find the enthalpy of reactions because enthalpy is a state function, so it doesn't matter in which method we use, the numbers should be the same. So one of these methods is by using the bond enthalpy, which is the enthalpy that you get when you break a bond of 1 mole of a gaseous molecule. So if we have a substance that is a gas, if we don't have a substance that's a gas, we have to turn it into a gas, and then we break the bond, the bonds or bond of 1 mole of that substance. So this is the energy we have to put in to break a bond. Now I want you to remember that breaking bonds is endothermic. So we can think about the enthalpy of the standard enthalpy of the reaction. That it's standardized because the bond enthalpies are also standardized. It's the sum of the bond energies or bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. Basically, we can think about it as the energy you need to put in minus the energy you get out, which should make sense when we think about endothermic and exothermic. So another way in which you can think about this is you can, and this is what I'm gonna show you this, and you can use the formula if you want to use the formula, or you can just think about it and not have to memorize the formula. So we have to put energy in to break bonds. Which bonds are we breaking? We're breaking the reactants. So when we break the reactants, we have to put the energy in for the reactants. So you're going to take the bond enthalpies of reactants and you're going to make them positive. So bond enthalpies of reactants are positive. So make those positive numbers. They will probably already be positive numbers. I would just make sure that you are keeping them positive, but they are endothermic. That's an endothermic process. Then thinking about bonds that we're making. So we get energy back or get energy out when we make bonds. Or not when we make bonds, but when bonds are made. That's because if you have a substance like H, like hydrogen, for example, so H is very unstable. So if we think about like a potential energy diagram, this is potential energy. HH would be a high potential energy. Then H2, making that bond, is a lower potential energy. So we have to, when we make that bond, we lose potential energy because it becomes more stable. So we're thinking about potential energy, high potential energy is less stable. Low potential energy is more stable. If I go from high to low energy, I lose energy, right? So that's exothermic. So hopefully that helps you wrap your mind around that just a little bit. So we get energy out when we make bonds. And what bonds are we making? We're making products. So we need to make the bond energy of the products negative because that's exothermic. And then once you have your positive bond energies of reactants and positive and negative bond energies of products, you're just going to add them up to get your delta H of the reaction. And RXN stands for reaction. If you have questions about this, feel free to take a picture of the screen and text me. So this slide is talking about the bond stability. I kind of already mentioned this. I spoiled it just a little bit. Basically, what I want you to think about we have to do here in this image is if we were going to run this reaction, this is these are hydrogens, the two white spheres, and then two chlorines, and we want to make HCl. So our reaction is here, our products are here. We can't, and I kind of alluded that we could just, here if we start with two atoms that are separate, you're just gonna make a bond. But if you start with some things that are already bonded, you have to separate them. So if I had some Lego pieces that were like this, and I needed to turn them into Lego pieces that looked like this, I would have to take apart these two Lego pieces. And in order to take them apart, we have to put energy in. So that's endothermic. So delta H here is positive. So the change in the enthalpy for that part is positive. Then you get your atoms just separated. Now that's very unstable. We just talked about how atoms are very unstable. When they're bonded, they're more stable. Then, if our products are more stable than the reactants, we're going to lose energy even past the reactants. So this is exothermic. Delta H would be negative. So overall, we have exothermic. So if we have enthalpy from reactants to products, so overall, delta H is negative because we went down from reactants to products. But in order to go down overall, we have to go up a little bit and then back down. So that's what we're representing when we talk about these bond enthalpies. To get this number, we have to add in the energy to do this, and then we subtract out the energy to go down, and then we get this overall. So it's a state function because we still wind up here and we still start here. We can't just go straight down because we don't have that information, but we can use the bond energies to figure out how much energy we got to put in, and then use bond energies to figure out how much energy we get out. But we still wind up in the same place. Same starting place to ending place is the same. So you'll see a table like this. You will, in a question on an exam or something, you won't have to memorize any of this. You'll be given these informations. And so you have certain bond enthalpies for certain bonds. We can make notes about, let's look at the N here. So single bonds, double bonds versus triple bonds. I want you to think about which bond is stronger, which bond takes more energy to break. Right, the triple bond takes more energy to break because it takes 945 kilojoules per mole to break, versus the single bond only takes 277 kilojoules per mole to break. And this should make sense. The more bonds we have, or the higher the order of the bond, right? So single bond is called first order, double bond is called second order, and triple bond is called third order. So the higher the order of the bond we have, the harder it is to break it, because there are more points of connection in a double bond or a triple bond. So we can see that bond strength in those numbers there. When we have an endothermic reaction, this is what it looks like. So we start our reactants off, and we have to break it apart. This is endothermic. So we put in energy to break apart our reactants. But in this case, because our products are less stable than our reactants, overall, we're endothermic because we put in a lot of energy and we didn't get back a lot of energy. So overall, we're going up. But again, it doesn't matter if we just go from here to here or if we go from here to here. As long as we get to the same place, we're good. So sometimes you can have exothermic reactions and sometimes you can have endothermic reactions, and it doesn't matter. So Let's see. What I want to do is go back to these real quick and show you how to do this with these numbers. So if we have H2 and Cl2, or yeah, H2 and Cl2 makes 2HCl. We have to draw the Lewis structures so we can see exactly what bonds we're making and breaking. I'm not going to draw all the uh, lone pairs, sorry. But I am going to draw out, if it says 2HCl, I'm going to draw 2HCls. This is just helpful to make sure that we understand that we have this many bonds. So we have our reactants, we have to add these. So we're going to add up, and I'd actually put a positive in front of these to make sure I don't mess it up. HH, if we look at the table, is 436 kilojoules per mole. And then we're going to add up ClCl, which is down here, 243 kilojoules per mole. And then we're going to subtract out our products. So when I'm thinking about how I'm going to type this into my calculator, I'm just going to say, all right, minus an HCl, which is 431. Minus another HCl, which is 431. Now you can say, I know minus 2 times 431, that's fine, but right now I just want to break it down into pieces. So we have to break these bonds. We got to put energy in to break those bonds. We're going to be making these bonds, so we get that energy back out. And then if you are following my method, you can just literally put all this in the calculator. I don't even write it down. I just put it in the calculator after I draw those Lewis structures. And so we should get a delta H of negative 184. It says 0.7, but I don't think you'll get the 0.7 when you do this. So let me just go ahead and tell you exactly what you'll get when you put this in the calculator. So in the calculator, again, I don't even write the numbers down like this. I just look at the numbers on the chart and I go, okay, HH is going to cost me 436. CL is going to cost me 243. HCl I get back, so subtract 431. Another HCl I get back, so I subtract 431. It's like budgeting. 183 is what this gives us. And we can see that it's very close to the actual value that they're showing us at the bottom right here. And it just depends on the significant figures of the table that you're given. So why don't you try for this one, 2NH3 goes to N2 plus 3H2. Why don't you try that one, pause it, and then come back. All right, let's try this one. So NH3s look like this, and I'm going to draw 2 of them so that I can accurately count how many bonds are there. You don't have to draw 2 of them. You can just say, hey, I'm going to draw 1 and then double it. That's fine, but for the purposes of practice, we're going to do that. And then N2 is a triple bond, and then 3 H2s. So for my reactants, I have 1, 2, 3, 4, 5, 6. So plus 6 NH bonds. I see HN here is 391. And then for my products, minus an NN triple bond, 945, minus 3 times HH, which is 436. And then I'll just put that in my calculator. So 6 times 391 minus 945 minus, and then I always put parentheses in my calculator when I'm doing anything that I think the calculator might get confused about. I know the calculators generally do order of operations, but on a test, I just don't trust myself to type it in correctly. So I'll put parentheses around anything that I think I might need it for. So I get 93 And then I dropped my units to do this just to fit it here. But of course, your units are going to be the same. We didn't really do anything with the units there. So my delta H of the reaction will be 93 kilojoules per mole. Let me put my little standard on this one. And you can see that's very similar to the 91.8 that we get here. All right, I want you to try this one. I'm going to show you just here. I want you to try drawing the Lewis structures for this one at the very bottom down here. Try drawing the Lewis structures and use this table here to help you out here. I'll zoom in on the table so you can take a screenshot if you want to. All right, pause the video and try to work that out. So hopefully you paused and worked it out. Here are your Lewis structures. We have to break 4 CHs and 2 O2s. We got to make 2 CO bonds, and we got to make 4 OHs. And so if we just add these up, now they're showing you how they use the formula, right? So the total of the, total of the reactants minus the total of the products. However, what I'm doing is just actually distributing the negative sign. The reason why I like to do this is because I find that sometimes students will subtract the first number for the products, but then they don't subtract the second number for the products because they don't put it in the calculator correctly to have that negative distributed. Or people try to add up a total number here, add up a total number here, and then subtract them, and that just takes a whole lot of time that you don't need to take. So in my professional opinion, just subtracting out each of the products and adding each of the reactants is a lot faster and will keep you from accidentally making a mistake in the distribution here. But you're more than welcome to use the formula. So if you have questions, please let me know, and we'll see you in class.